We are hungry for energy. Experts predict an up to 2 times increase in global energy demands over the next 30 years. And for the past few decades, we've been feeding our planet some pretty unhealthy food, which has made it all hot and gassy. One thing I love just as much as my research is cooking. So perhaps I can explain my work through a culinary lens. So, our planet has a clear need for cheap, green electricity. That's where my research into fusion energy comes in. It's green food with all kinds of benefits. There's no greenhouse gas emissions. It doesn't matter whether the sun is shining, the wind is blowing, or water is flowing. Fusion can be anywhere, anytime. The fuel is practically limitless. And unlike fission energy, there's almost no radioactive waste. To make fusion, we need an ingredients list and a recipe. And the ingredients are simple. It's just hydrogen gas. We can first ionize our gas into a plasma, which is basically just a soup of ions and electrons. We then heat our soup up to 100 million degrees Celsius, because nobody likes a cold soup, and contain or confine it in a bowl. Inside our bowl of soup, ions crash into each other and fuse, releasing a lot of energy, something that's even predicted by Einstein's E=mc². Now, people have tried dozens of approaches to make fusion work, but none have won the title of Star Baker just yet. One of the biggest obstacles has been confining the soup in its bowl. My research focuses on one often overlooked approach, the centrifugal mirror. This simple concept combines a strong electric and magnetic field to rotate our soup faster than the speed of sound, which leads to all kinds of benefits, including better confinement. In fact, my team and I have built a 20-foot-long fusion reactor to prove those benefits, and it's already working just like we predicted. One of the biggest challenges moving forward is that this machine requires an electrically insulating material that can withstand heat flux higher than that on the surface of the sun and particle bombardment that can rip apart steel. I've chosen and have been testing a material called hexagonal boron nitride to determine whether it can survive in this harsh environment. My modeling predicts that it has good resistance to both heat and particle damage. Next, I'm going to put samples of this material inside our machine and characterize changes to the material. If I'm successful, that puts us one step closer to feeding our planet that healthy green fusion food.